Let's talk about what conic sections are. The word conic, notice, has the word cone right in it. And in fact, this is where the word conic section comes from. Every one of these 5 conic sections can be seen as a cross section of a cone, a double cone, where the tip, you see that this is a double cone here. So let's take a look at what that looks like. If I take a cross section, I can make a circle as long as that cross section is going perfectly parallel with the top portion of the cone. So if I took that cross section and I turned it around, I'd look at it, that'd be a perfect circle. No, I'm not drawing a perfect circle on there, but you'd understand that would be a perfect circle. If I took the cross section of this, it would be a circle if I looked at it from the top. So that's a circle. An ellipse, notice that I can get an ellipse if I take the cross section of this cone at an angle. I would get an ellipse. So looking at it from the top view, if I took the cross section of that, I would get an ellipse like that. I would get a hyperbola by taking the cross section vertically like this. I would get a hyperbola, and again the hyperbola looks like this. That's a hyperbola. I'd get a parabola if I took a cross section of that cone skewed, not going through both parts of this cone. I would get a parabola. And then I would get a point if I took a cross section. Usually they don't even talk about points, but technically if I took a cross section right there, I would get a point. You also can get different kinds of parabolas where they're not perfectly vertical and horizontal, but those all are from cross sections of a cone, and hence the word conic sections. So let's talk about the geometric definitions. So that's the pictorial understanding of a conic section, but now let's talk about each one of these, the first 4, geometrically speaking, because there's also a geometric definition, and it has to do with a set of points. So a circle is the set of all points whose are units from the center. So here's the center point, and if you know this definition, if I go r units away, I'm going to get all of the points on that circle. And so that's what a circle can be defined as, the set of all points r units away from a fixed point, which is called the center. An ellipse is similar to that. It is, but instead of going to one point in the center, here's your center h comma k, you're actually breaking it off, and these are called foci. These are the 2 foci, or each singular would be focus. Those are the foci. So the geometric definition of an ellipse is the set of all points, the sum of whose distances from the 2 foci is constant. So this distance plus this distance is equal to a constant, let's say 10. And if that distance plus that distance is also 10, that distance plus that distance is also 10, that distance plus that distance is also 10, etc. That distance plus that distance is also 10. So that's the geometric definition of an ellipse, and you'll see the equation for a circle is right there, and you'll see that it looks very similar to the equation of an ellipse. The only difference is I have 2 radius. I have a vertical radius and a horizontal radius. The vertical radius, let me draw this in purple. The vertical radius is from the center to there. That's the vertical radius. The horizontal radius, so that's r sub y. The horizontal radius, I'll draw this in light green, is from here to there. That's the horizontal radius. That's r sub x. Okay? So let's talk about, oh, and by the way, there is a relationship between these radii and the focal radius, which we call that normally, I'll do yellow for this. This right here is the focal radii, and we usually call that C. And there's a relationship between r sub x and r sub y and C, and that relationship is a Pythagorean relationship. So the relationship is, you'll notice that, whoops, I did that wrong. The largest of these 3 is actually r sub x because it opens sideways. Oops, I did that again wrong. So this right here should be r sub x, and this is r sub y. And a squared plus b squared equals c squared, that's a Pythagorean identity. And that holds true for an ellipse and hyperbola, both of them. And the ellipse, if you'll notice, the focal radius is smaller than the horizontal, than the major, they call it the major axis, that green line that I drew in earlier. There's your green line, r sub x. So since that's the largest value, that's going to be like the hypotenuse of your right triangle if you think of the Pythagorean identity. Remember, Pythagorean identity has to do with triangles. All right. So here's a hyperbola. Notice that the ellipse definition was the sum. The hyperbola definition is the exact same, except it says the difference. And so I won't bore you with the details, but your hyperbola is going to look like this. It's going to open sideways. They're not two parabolas. These are actually asymptotes, slant asymptotes that the two shapes approach. But there's your sideways opening parabola. Notice that the x term is positive, and here's your up and down opening. Would be this one, because the y term is positive right here. And again, we're going to have another relationship. The relationship, your focal points, by the way, are on the inside here. There's your focus. There's two foci, just like with an ellipse. That distance from the center to the focus, which again we call C, notice how that distance is going to be the biggest now. So your c squared equals rx squared plus ry squared. That's a relationship. It's the Pythagorean relationship there. And next we'll talk about parabolas. The parabolas, geometrically speaking, are the set of all points equidistant from a fixed line called the directrix. Here's my directrix down here, and a fixed point called the focus. So all of the points, you don't really think about it like this when you do it, but that's what it is. Every point that's right between that distance and that distance are equal. That distance and that distance are equal. That distance and that distance are equal. And what you're going to get is a parabola. Like that, if I drew it correctly. That is the geometric definition of a parabola. And that has to do with, a lot of books use the letter P to be the focal distance. I was saying C for the other ones, but for this they use the letter P. That distance is P, as is that distance right there. It's the distance from the vertex of your parabola, which is right there on the bottom. There's your vertex. Right there's your vertex. The distance P right there is the same for both of those. It's the distance from your vertex to your directrix. So if I move the directrix closer to the if I made P smaller, then your parabola would be steeper. If I made P bigger, like if P was 5, it'd be a pretty wide parabola. So the P tells you how steep your parabola is. And that is, again, your geometric definitions along with some of the formulas for your 4 conic sections, not including the point, which is an obvious one. A point's just a point. There you go.